Okay, so now we're going to talk about symmetry with polar graphs. And just like back in college algebra, we had tests to check for symmetry about the y-axis or symmetry about the origin. We are now going to look at tests to check for symmetry with polar graphs. Now there's three different tests. There's a test to check for symmetry with respect to the line theta is equal to pi over 2. And that is basically the axis that we think of as the y-axis. So in figure A, we're looking at this line right here. That is the line theta is equal to pi over 2. And if we want to see if there's symmetry with respect to theta is equal to pi over 2, then what we're going to do is we're going to replace r and theta with negative r and negative theta. And if we get the same equation back as what we started with, then we'll know that we have symmetry about the line theta is equal to pi over 2. And if you look at this figure, what this shows is if I have a point here, when an angle sweeps open, I'm going to have the same point over here if this angle sweeps open the same amount, but from the negative x-axis. So there is a reflection across what we think of as the y-axis, but really is the line theta is equal to pi over 2. If we're checking for symmetry with respect to what we think of as the x-axis, that is actually called the polar axis, and that is this axis here. So this is the polar axis. So if we want to check to see if we swing open an angle in the positive direction, and then we swing open the same angle but in the negative direction, and we get that same point, then we have symmetry with respect to the polar axis. And how we test for that kind of symmetry, we replace r and theta with r and negative theta. And if we get the same thing back as what we started with, then we have symmetry with respect to the polar axis. In the last test, symmetry with respect to the pole. The pole is what we think of as the origin. It's just that center point. That's called the pole. And if we have symmetry with respect to the pole, that means if we open an angle of theta in one direction, and then we add another 180 degrees to that, we're going to have the same point on the other side of that pole. And the way we check for symmetry with respect to the pole is we replace r and theta with negative r and theta. Now in the book, some of the examples they show you, they test for all three symmetries every single example. But what I like to do to try to limit or minimize extra work that we don't need to do, I like to look at the graph first and narrow it down. So in the first example for checking for symmetry, we've got the equation r is equal to 1 plus cosine theta. So what I like to do is I like to graph it first since I'm a visual person, and rather than do all three tests for symmetry, I narrow it down to the ones that I think I need to check. So when I graph this on my calculator, this is the picture I get. It looks kind of like a sideways heart. And when I look at that, I notice that if I were to fold it along what looks like the y-axis, or what we think of as the y-axis, which is the axis theta is equal to pi over 2, if I try to fold it along that line, it doesn't line up. So we don't have symmetry with respect to theta is equal to pi over 2. If I look at the origin, if I have a point over here and I add 180 degrees to it, I should have the same point over here and vice versa. If I have a point over here, I should have a point over here. This to me does not look like symmetry about the pole. So if you're not 100% sure, then you should definitely do the test. But to me, this looks like symmetry about what we think of as the x-axis or the polar axis. So that is the test that I'm going to do. So if I look back up at my rules, if I want to check for symmetry with respect to the polar axis, I need to replace r theta with r negative theta. So I'm going to take r theta and replace it with r and negative theta and see if I get the same equation back. So if you notice, r doesn't change, but I replace theta with negative theta. So I'm starting with the equation r is equal to 1 plus cosine theta, and I am going to replace theta with negative theta and see if I get the same thing back. Now, if you think back to previous section when we talked about even and odd trig functions, if you recall, cosine is an even function, which tells me cosine of negative theta is the same as cosine theta. So now I can replace cosine of negative theta with cosine theta using even properties, and I get the same equation. So that means we definitely have symmetry with respect to the polar axis. Okay, looking at example B, we have the equation r is equal to 2 sine theta. When I look at that graph, I get a picture that looks something like this, like a shifted circle. The center has been shifted from the origin up. And so that to me looks like it would be symmetry about the line theta is equal to pi over 2, or what we think of as the y-axis. So I'm going to check for symmetry about the y-axis. I don't see any symmetry about the pole or about the polar axis. So I'm going to come up here and look at my rule. And my rule says if I want to check for symmetry about the line theta is equal to pi over 2, I'm going to replace r and theta with negative r and negative theta. So I'm going to replace r and theta with negative r and negative theta. So I'm starting with the equation r is equal to 2 sine theta. And I replace r with negative r. And I replace theta with negative theta. And if you recall, sine is an odd function. And if we think back to the properties of odd functions, that tells me that sine of negative theta is the same as negative sine theta. So I'm going to replace sine of negative theta with negative sine theta. And then when I divide both sides by negative 1, I get the same thing as what I started with. So that tells me I have symmetry about the line theta is equal to pi over 2. Okay, last example. I have r squared is equal to 4 sine 2 theta. Now, because this is an r squared, and our calculator only graphs it if its r is equal to, and then you plug in the rest of the right-hand side of the equation, I have to square root both sides and solve this for r. So I get r is equal to plus or minus the square root of 4 sine 2 theta. And so when I put this in my calculator, I have two parts. I have to put in one line as positive square root of 4 sine 2 theta. And then I also have to put in negative square root of 4 sine 2 theta. So I have two parts to that equation. When I graph it, it is going to look like an 8. Let me see, I'm not doing a very good job of drawing this. It's going to look like a tilted 8. Now, if I fold that along the polar axis, or what we think of as the x-axis, it's not going to be a reflection. If I fold it along the y-axis, or the line theta is equal to pi over 2, there's going to be no symmetry there, but there may be symmetry about the pole, or what we think of as the origin. So I'm going to do a test for the pole, symmetry about the pole. So if I come up here and I read, it says a graph is symmetric with respect to the pole if we replace r and theta with negative r and theta and we get the same equation back. So I'm going to replace r theta with negative r theta. Notice theta stays the same. We're only replacing r with negative r. And if I start, here's my original equation, r squared is equal to 4 sine 2 theta. And if I replace r with negative r, because that negative r is squared, I have negative r times negative r, I'm going to get the same thing back. So that tells me I have symmetry about the pole because I get an equivalent equation.